So this is the gas laws. We're actually going to look at 4 of the gas laws. Boyle's Law, Charles' Law, Gay-Lussac's Law, and the combined gas law. Before we start looking at the gas laws, I want to remind us that there are 4 main variables of gases that we look at. P for pressure, V for volume, N is for number of moles, which is the amount of gas, and T is for temperature. And all 4 of these variables can change, and when 1 or 2 of them change, it affects the other ones. It's kind of a cause and effect type relationship. With these gas laws that we're going to look at, the N, the number of moles of gas, is actually constant in all of these. So in gas laws, when something is constant, you kind of ignore it. You don't consider it because it's not changing. So what's going to happen with all 4 of these laws is P, V, or T are going to change. In the first 3, 1 is going to stay constant and 2 are changing, and in the combined, all 3 are changing. So when we look at Boyle's Law, Boyle's Law is P1, V1 equals P2, V2. So the first pressure and volume and equals the second pressure and volume. The 1s are usually for the initial set of conditions, the 2s are for the change. Notice this is multiplication straight through. For Charles, you're going to do volume and temperature comparison, so V1 over T1 equals V2 over T2. Notice these are fractions. You set them equal to each other and you cross multiply to solve. Gay-Lussac's law is pressure and temperature, so it's P1 over T1, P2 over T2. What I want you to look at real quick is how Boyle's law is a straight multiplication, whereas Charles' law and Gay-Lussac's law, they are fractions. And there's a reason for that. Remember that in Boyle's law, pressure and volume are inverse or oppositely related, meaning as pressure goes up, volume goes down, and vice versa. In both Charles and Gay-Lussac's law, the volume and the temperature and the pressure and the temperature, they're both direct. They're directly related, which means the same. So as one goes up, the other one also goes up. What I want you to notice is that can help you remember the relationship. So Boyle's law is all multiplication, it's opposite. Charles' law is fractions, it's the same. And then the combined gas law does just what it says. It combines all 3 of the top, so you have pressure, volume, and temperature all changing at the same time. So what we're going to do first is we're going to read the problem and we're going to solve some gas law problems. One of the hardest things might be figuring out which equation to use. So what I'm going to do is I'm going to do a technique where I write what I know or what the problem tells me as I go. It's called writing your knowns. And that really helps you figure out what equation is going to work. So watch how I do this. So it says a sample of gas in a 2-liter container. I know that liter is a measurement of volume. So I'm going to write a V and I'm going to write 2 liters. At a pressure of 740 mmHg. So I have a pressure. Notice I'm writing the units down because the units still have to match. That rule's still in effect. What is the new pressure? So what I want you to see here is this word new. It indicates a change. So what that tells me is this volume and pressure are the 1s, the initial conditions, and what I'm going to look for is the 2, the new condition of pressure of the sample if the volume is reduced, again a change, so that tells me the V2 is 1.25 liters. So again, it's very important to read, it's very important to write down the knowns as you go. Because what happens here is I see the only 2 variables that are changing are volume and pressure. So the only equation that's going to work here is Boyle's law. I can't use Charles' law, I can't use Gay-Lussac's law because there's no temperature. So if I don't have a T, I can't use the equation with the temperature in it. Rule still applies. Units have to be just the same, so liters, liters, we're all good to go. So then I just plug in. So I'm going to do the P1, 740 times 2. I'm solving for P2. I usually just write it as P2 as the variable. If you don't like that, you certainly can write it as an X. So what I'm doing mathematically here is I'm going to multiply 740 by 2 and then divide it by 1.25, basic algebra, to solve for P2. And I get 1184. And then remember my units have to match. So I know my unit, my answer unit is going to be the same as the P1, which is mmHg. So if you write those knowns down as you go, it really makes this process a lot easier. So let's move on to the next one. A gas is collected and found to fill 2.85 liters at 25 degrees. So I have, again, a liter, so I have a volume, 2.85 liters, and then I have a temp here, 25 degrees. Now we're going to remember, for gas laws, all temperatures have to be in Kelvin. And if you don't remember, to go from Celsius to Kelvin, you very simply add 273. So I'm just going to do that right away. I'm just going to convert my temperature to Kelvin so that I don't forget. They have to be in Kelvin. That's the only unit that has to be something. Now, what will be its volume at 0 degrees? So again, this indicates a change. So these two conditions are my 1. It's asking for the new volume. So there's your question mark. And then my new temperature, my T2, is 0 degrees Celsius, which simply goes to 273 Kelvin. Now again, I have V's and T's. The only equation that will work is Charles' law. I can't do anything with pressure, so that eliminates every other one. There is no pressure, I can't use that. So it is V1 over T1 equals V2 over T2. So it's going to be 2.85 over 298. I'm solving for V2 over 273. So again, you're going to remember, you're going to cross multiply here. Cross multiply to solve. So when you cross multiply, you're going to do 2.85 times 273 equals 298 times V2. Then you're going to use your algebra and solve for V2, and you're going to get 2.61 liters, and I know it's liters because the initial volume was liters. Same technique as we go, same technique. You're going to write the knowns on the side. So it says 10 liters, so I know that's a volume, 10 liters, of a gas is found to exert 97 kPa. I know kPa is a pressure, so I'm going to write that down. At 25 degrees, there's a temperature. Again, I'm going to immediately turn 25 degrees to Kelvin, so I don't forget to do it later, 298 Kelvin. What would be the required temperature in Celsius? Now this is a key. When it asks for a temperature in Celsius, you still have to make the initial change to Kelvin, and then you have to change it back. You only have to change it back to Celsius when it stipulates that. It is a new temperature, so I know this is going to be a 2, which means that one has to be the 1. If there is a change in pressure, so I know that's going to be a P2 to 1 atm. So I have a whole lot of things going on in this problem. One thing I want to point out is the volume. The volume says at the beginning it's 10 liters. What I want you to notice is volume isn't mentioned again. It's not changing. So whenever anything in the gas laws doesn't change, you ignore it because it is constant. Okay, with a circle is a symbol for constant. So because the volume's kept constant, even though the problem mentions it, it's still not considered in the equation. So you're just going to cross it out. And then I know this initial P had to be the P1 because it mentions a change to ATM. I'm going to notice my rule is being violated. The first pressure is in kPa, the second pressure is in ATM. Again, doesn't matter what you change, but go with the easiest one. The easiest one would be the ATM to kPa because you don't even have to do any math. You just know that 1 ATM equals 101.3 kPa. Now, since we eliminated that volume, we know that the only equation that will work is going to be Gay-Lussac's law. So it's P1 over T1 equals P2 over T2. And then I'm just going to plug in 97 over 298 equals 101.3 over T2 that I'm solving for. Again, you're going to cross multiply and then you're going to solve. So you're going to multiply 97 times T2 equals 298 times 101.3. My T2 is then going to come out to be 311. This is going to be 311 Kelvin. Because this number was in Kelvin here, 298, the answer is going to be in Kelvin. So to get it to Celsius, you do the opposite. So if you add 273 to turn it into Kelvin, you subtract 273 to turn it back to Celsius, and you get 38 degrees Celsius. You only have to do that change. You only have to turn it back to Celsius if the problem stipulates. Okay, let's do one more. This is a 2-liter sample of gas. So again, I have a volume. It's collected at 25 degrees Celsius and 745 mmHg. So I have a T. Again, right to Kelvin, so I don't forget to change it later. So 298. And then I have a pressure of 745 mmHg. What is the volume? So it's asking me for the volume. So this has to be the 2. So I know this is a 1 at STP. Remember, STP stands for standard temperature and pressure. You have to know what it stands for, and you have to also know the values. The value of standard temperature and pressure is going to be 0 degrees Celsius or 273 Kelvin, and the pressure is going to be 1 atm. Now, since those are new conditions, they get 2s, which means my initials are going to be 1s. So I have all these T's and P's working here. It's going to have to be combined gas law. They're all changing. So if you see the difference between the first problem, the volume didn't change. It just stayed 10 liters. In the second problem, the volume's changing, the temperature's changing, and the pressure's changing. And that's why you need all 3. I do have to make sure my pressure units agree. They do not at this point. But again, it's just easy to take 1 atm because that equals 760 millimeters of mercury. So I'm doing combined gas law this time. They're all going to come into play, all 3. So it's P1V1 over T1 equals P2V2 over T2. I'm going to plug in. So 745 times 2 over 298 equals 760 times V2 that I'm solving for, and 273. So again, I'm going to cross multiply. I'm going to cross multiply everything. This whole thing times this whole thing. So when I get these numbers, I'm actually going to write them out for you. They're kind of big, so you know. So when I do 745 times 2 times 273, I get this big number. And then when I do 298 times 760, I get this big number. Don't forget that's multiplied by the V2. Then I just divide and solve for V2, and I get 1.80 liters. Again, I know it's liters because my initial volume was in liters.